let's get the whole problem done. So it's not just a matter of using u substitution, but let's change the variable over to u, and then let's actually take the antiderivative and use the fundamental theorem of calculus and come up with the actual area. Okay, so for problem number 1, we have this messy function right here, x times the quantity x squared plus 1 cubed dx. We're trying to find the area between this function and the x-axis from x equals 0 to x equals 1. There's a lot of work going on there. Let's go to u substitution so we can come up with an easier antiderivative rather than cubing this binomial and then distributing an x. Right? So u is going to be equal to our inner function. We can see that u is going to be x squared plus 1. Making du equal to 2x dx. Okay, so we have the x and the dx, we don't have the 2. Like the previous problem, we need a 2 on the inside and a 1/2 on the outside. All right, so this is going to be equal to the integral, and now x squared plus 1 is replaced by u, so we have u cubed. The 2x and the dx are replaced by du. We have the 1/2 out front, and we've changed our differential, we've changed our integrand. Now we need to change over our bounds. So we have to square our old bounds and add 1. 0 squared plus 1 is 1. 1 squared plus 1 is 2. So we're going to take our new bounds to be 1 and 2. We're going to plug those bounds in, but not yet. First, we need to antiderive. What happens when we antiderive u cubed? Yeah, it becomes u to the 4th over 4. So what we have here is 1/2 times u to the 4th over 4, and that's being evaluated from u equals 1 to u equals 2. Okay, we're going to plug the 1 and the 2. We're not going to plug in the 0 and the 1. We're not going to go back to x. We're just going to work off of our new bounds. We'll get the same answer. Could you go back to x? Yes. If you do, you have to go back to the old bounds of 0 and 1, and then you're going to plug in those values, and you're going to get the exact same answer as if you just plug in the 1 and the 2. So save yourself some time and effort, and just plug the 1 and the 2 into this antiderivative. Now we see over a half, or over 2 and over 4, so really we're dividing by 8, correct? So what we have here is 2 to the 4th over 8 minus 1 to the 4th over 8. Okay, and that's a correct answer if we don't simplify it. If you choose to simplify it, 2 to the 4th is, what, 16, correct? 2 times 2 times 2 times 2. So we have 16 over 8 minus 1 over 8, which means we have a total of 15 over 8. For our second problem, our inner function is our exponent of e. So u is going to be equal to 3x, which means du is equal to 3 dx. We have the dx, we don't have the 3, so we're going to put the 3 on the inside and the 1/3 on the outside. Making our changeover, we have 1/3 times the integral of e, and then 3x is replaced by u, and the 3 dx is replaced by du. So we have e to the u du. That's a nice, easy antiderivative to take. We have to change our bounds. Our old bounds are 1 and 2. We have to triple them. 1 tripled is 3, 2 tripled is 6. There's our new definite integral. Take the antiderivative. So we have 1/3 e to the u, and that's being evaluated from 3 to 6. Plug in the 6 minus plug in the 3. So we have 1/3 e to the 6th minus 1/3 e cubed. That's as far as we need to go.